All right, today we're jumping into a really cool reinforcement learning framework called Parallel R1. And its whole purpose is to teach large language models a skill that, frankly, is second nature to us, but a huge hurdle for them. How to think in parallel. How to explore multiple ideas at once instead of just plodding down a single path.
So think about it. For the last few years, the big driver in AI reasoning has been sequential thinking, right? Chain of thought is the perfect example. But what if that whole linear process is actually a bottleneck? What if forcing a model to pick one path and stick to it is causing it to miss better, more creative, or just plain correct solutions? That's the big question here, and it really sets the stage for a totally new approach to AI reasoning.
And that new approach, as you might have guessed, is all about parallel thinking. And look, this is not just some academic exercise. Google just recently talked about how its Gemini model's incredible success at the International Mathematical Olympiad was, in part, thanks to this exact capability. It's a huge signal that moving beyond one thought at a time is probably the next major frontier we need to cross.
So, what do we actually mean by parallel thinking? Well, the idea comes straight from cognitive science. It's what our brains do naturally. We weigh different options, explore a few what-ifs, simultaneously before we commit. For an AI, this means instead of getting locked into its very first idea, which could be a dead end, it can spin up several lines of reasoning at the same time, compare them, and then move forward with the best one. It's all about avoiding that early critical mistake.
Okay, so here's the catch. You can't just flip a switch and tell a model, hey, think in parallel now. This kind of behavior is basically nowhere to be found in its original training data. So you have this massive problem. How in the world do you teach an AI a completely new way of thinking from absolute scratch? This is what's known as the cold start conundrum, and it is the single biggest challenge this Parallel R1 framework was built to solve. Now, you might think of two ways to tackle this. The first is supervised fine-tuning, or SFT. This is basically like giving a student a stack of solved exams and telling them to memorize the answers. Sure, the model learns to copy the patterns it sees, behavioral cloning, but it doesn't understand the strategy. It can't generalize. The other route is reinforcement learning, RL, which is more like telling the student to figure out how to solve the problems on their own. It's way more powerful, but it runs into that cold start wall. If the model has never even tried to think in parallel, it won't even know it's an option during its exploration phase. It's a classic catch-22.
And the data makes this brutally clear. When the researchers tried to just prompt a powerful model to generate parallel thoughts for easy math problems, it did pretty well, an 84% success rate. But when they gave it complex problems, it completely fell apart, a 0.0% success rate. This is the smoking gun. It proves you can't just prompt your way into this. You need a fundamentally better way to teach this skill.
And that is exactly where the Parallel R1 framework comes into play. You can think of it as this really clever, multi-stage playbook that's been specifically engineered to crack that cold start problem and actually instill a parallel thinking skill that actually works in the wild.
The solution is this awesome 3-step progressive curriculum. It's basically a crawl, walk, run approach. First, in step 1, you use a little SFT on super simple math problems. The only goal here is to teach the model the syntax, what parallel thinking even looks like. Then, in step 2, you switch to a bit of reinforcement learning. Still on easy stuff, just to get the model comfortable and stabilize that new behavior. And finally, once that foundation is solid, you unleash it with large-scale RL on much harder, more general problems. That's where it learns to actually generalize the skill.
Of course, none of that would work without some very clever reward engineering. See, the model could just ignore this new skill and keep chasing the easy reward for just getting the right answer. To prevent that, the researchers used an alternating reward scheme. 80% of the time, it gets rewarded for accuracy. But for the other 20%, there's a special tiered reward. If it gets the correct answer without using parallel thinking, it gets a +1 reward. But if it gets the right answer using the parallel structure, it gets a bigger reward, +1.2. It's a small but constant nudge, encouraging the model to value and use this new tool in its toolbox.
So, the big question, did it actually work? The short answer is yes, absolutely. But honestly, the final scores aren't even the most interesting part. The really fascinating discovery is how the model's strategy, the way it uses parallel thinking, completely changes and evolves as it gets smarter.
Okay, but first, let's look at the numbers. Across the board on several math benchmarks, the models trained with this Parallel R1 method pretty handily beat the strong baseline. You can see the Parallel R1 scene model hits an average score of almost 49, which is a really solid jump from the baseline's 45. So, check. The framework is definitely effective at improving performance.
But beyond just getting better scores, the researchers noticed something much deeper. The way the model deployed its new skill was changing. It wasn't just learning a static trick, it was developing a dynamic strategy that adapted as its own confidence and competence grew. This is where it gets really cool.
And this timeline just lays it out perfectly. Early in its training, when the model is still a bit unsure of itself, it uses these parallel blocks right at the beginning of a problem. It's essentially brainstorming, right? Using exploration to try and find any path that might work. But later on, as the model gets better and more confident, it flips the script. It becomes more efficient. It'll first come up with a single answer it feels good about, and then it uses the parallel block at the very end, almost like a sanity check, a way to verify its work from multiple angles before giving the final answer.
And that incredible observation, that shift from exploration to verification, leads directly to the paper's single most profound idea. It's an insight that could genuinely change how we think about training AI models from now on. They call it the Scaffolding Insight.
So here's the big reveal. What if the real value of parallel thinking isn't as a skill in the final model, but as a temporary training scaffold? It's like training wheels for a bike. You don't want to use them forever, but they're essential for learning the core skill of balance. The theory is that by forcing the model to explore these different paths during training, you guide it towards a much more robust, general reasoning ability that it might never have found on its own.
And to put this theory to the test, they used this scaffolding approach on a really challenging math competition benchmark, AMY 25. The result? A staggering 42.9% improvement over the baseline model, hitting a peak accuracy of 25.6%. And here's the kicker. This massive gain happened even as the model naturally stopped using the parallel structure in its final answers. It's the ultimate proof that the temporary training wheels built a permanently better bike rider. And for those of you actually building things, the possibilities here are huge. Imagine a code gen model that explores multiple API calls at once, or a drug discovery model that evaluates different molecular pathways in parallel. This is a big deal.
Which leaves us with one final, very provocative question to chew on. This research strongly suggests that the best way to build smarter models might involve teaching them skills and structures that we don't even want them to use in the end. So if these temporary scaffolds can build a permanent, superior skill, it really forces us to ask, what else should we be teaching our models, with the specific intention of having them forget it?